You're at the absolute bottom of a lift. The weight feels impossibly heavy, and the bar stops moving. People assume the muscle tissue has reached its absolute mechanical limit. The muscle tissue hasn't failed at all. The central nervous system simply cut the power. Your body runs a strict autonomic survival protocol. When it senses extreme strain, it intentionally shuts down motor unit activation to protect the tendons and joints from perceived structural damage. This creates an artificial ceiling. There is a massive gap between the point where you feel you failed and your tissue's actual biological capacity to handle tension. Accessing that hidden capacity requires a process called neurological de-inhibition, hacking the survival software that dictates your limits. You do this by deliberately forcing the body into extreme, fully stretched ranges of motion while under heavy, uncomfortable loads. If you drop the weight the moment your nervous system throws its warning plaudix, the most potent stimuli for tissue adaptation remain completely untapped. Mastering muscle growth requires you to subjugate your nervous system's instinct for self-preservation. Your muscles rely on two internal sensors, proprioceptors, to monitor the mechanical stress of every movement. The first sensor is the muscle spindle. It detects rapid changes in muscle length and triggers the stretch reflex, forcing a contraction to prevent you from overstretching. The second sensor is the Golgi tendon organ, or GTO. It monitors extreme mechanical tension pulling directly at the tendon junction. Look at this schematic comparing the two sensors. The muscle spindle sits parallel to the muscle fibers, reacting to length, but the GTO sits directly in series at the muscle tendon junction, reacting to tension. During a heavy lift, they fight for control. The GTO has a built-in safety switch called autogenic inhibition. When mechanical tension crosses a critical threshold, the GTO sends an inhibitory signal that instantly forces muscle relaxation to prevent the tendon from tearing. But that shutdown threshold is malleable. By exposing the tissue to sustained heavy loads, specifically over 85% of your 1-rep max, you can systematically push that red line higher. Heavy loaded stretching actively desensitizes the GTO. You are reprogramming your nervous system to tolerate extreme localized tension without initiating an autonomic shutdown. Once you've successfully bypassed the GTO safety override, the effects plunge straight down to the microscopic level of the sarcomere. This is where we meet titin. It's a massive, spring-loaded structural protein designed to bear extreme passive tension when muscle fibers are pulled apart. In this diagram of a single sarcomere, you can see how the titin filament is anchored. It acts as a physical bridge, tethering the Z-disc to the thick myosin filaments. When you force a muscle into a heavy, loaded stretch without GTO interference, the sarcomere gets pulled to its extreme edges. The titin spring violently elongates, absorbing the brunt of the mechanical strain. Embedded directly on that stretched titin filament is a specific cluster of proteins called the N2A MARP signalosome. It acts as a molecular stress sensor. The extreme mechanical strain physically warps this signalosome. That physical deformation forces the release of a chemical cascade, the mTORC1 pathway, which ignites the protein synthesis required for muscle growth. Pure mechanical tension must be sustained long enough to physically deform titin. That physical strain is the required input to initiate chemical anabolic signaling. Standard training makes existing muscle fibers thicker, but the extreme mechanical strain placed directly on the titin filament triggers a completely different, highly specialized architectural adaptation. As you can see in this model, the muscle builds new sarcomeres in series, linking them end to end. The muscle fascicles physically lengthen, a process known as longitudinal hypertrophy. The body executes this structural addition to normalize the extreme passive tension it just experienced, ensuring it can confidently handle that same stress more efficiently the next time. This structural change increases both the muscle's overall stiffness and its capacity for force generation at long, stretched lengths. The body never initiates this architectural upgrade if you retreat the moment your internal sensors sound the alarm. Absolute biological optimization exists exclusively in the space beyond neurological comfort. It demands the deliberate suppression of our survival instincts to force structural evolution.